Hi, welcome to the Semantics lecture about existential quantification. Existential quantification, put simply, is quantification that asserts the existence of something with a property. And in a more formal sense, we'll see that it expresses a non-empty intersection between two sets. And in that sense, we can derive this sense of existence. So when we say existential, we mean something like a sentence like this, or a proposition like this: a dog is barking. The quantifying determiner and the phrase a dog is used in this sentence to assert the existence of some dog that is barking. And in that sense, it can be contrasted with the universal quantifiers like every or some, where we're talking about a whole class of dogs. Now, when we say existential quantification, right, we're doing semantics, what we want to understand is what this quantifier means. And to do that, we have to understand not just what it is, but what it isn't. Right? And we saw that existential quantifiers, like other quantifiers, don't refer to things of type E because they don't behave the same way, right? They don't have the same contradictions. They they have, movement affects their meaning, and they get scope and things like that, and they fail the law of exclude middle, and so forth. There are a lot of different reasons for saying that quantifiers do not denote things of type E. But what do they mean then? Well, one alternative is that instead of denoting things of type E, they denote sets of individuals. We could say, oh, there's a set. That a dog is barking means some set of dogs with one member is barking. Or if we say some dogs in the plural, some dogs are barking, does that mean that we're saying that referring to some particular set of dogs? And the answer is no. Quantifiers do not refer to sets. It's easy to think of them that way, especially with universal quantifiers. But it is dangerous to think of it that way because it's wrong. But it sounds like it could be right. But if you think about it for a moment, you'll see that it's wrong. So here's a good example of why. Again, entailments will show us. So if we say Arvo is barking, and let's say Arvo is the name of a dog, so it's a referential expression. Arvo is barking, Arvo is at the door. If both of those are true, then this conclusion is inescapable. Arvo is barking and at the door. Although it's a bit more natural to say Arvo is barking at the door. Now, this works because this is a referential expression. Arvo is in this set, Arvo is in this set, so Arvo is in both sets. Pretty straightforward. That works if you have a referring expression. It does not work if you don't. So let's see. A dog is barking. True. A dog is at the door. Okay. If those are both true, however, this does not have to be true. A dog is barking and at the door, or a dog is barking at the door. Why? Well, because the dog that's barking could be somewhere else. So these could be two different dogs. And so this entailment doesn't hold. So this entailment holds because if you're in one set, and if you're in set A and set B, you're in set A and B. But here, whatever dog this is in this set. Whatever dog this is in this set. But this doesn't have to be the same dog, which means it's not referring to that dog or to any dog, really. So in that sense, then, what does it mean? Right? If it doesn't refer to something of type E or of type ET, then what does it mean, and how do we get that? How do we get its meaning to compose with dog and barking? And so let's look at the syntax real quick. We have we'll say that it's a determiner, projects to a DP by taking the noun phrase as its complement. We'll say a dog. Pretty straightforward. Now whether this is a D or if there's a separate projection, Q for quantifier or something like that, that is an interesting question, and we'll for another time though. Right now we'll just say it's a D. A dog. Now, how do we determine what a dog means? So we have this phrase, a dog, and it will combine with is barking as a VP. And is barking is a property. It's an unsaturated property. So in the semantics, this is going to be lambda x and d sub e, bark of, we'll just say bark of x. We'll keep it simple. The sentence is going to be a truth value. It's going to be of type T. And this will be of type ET. So we need that's why we thought this was something of type E, but this can't be something of type E. It can't be of type ET either, as we've seen through the meanings. But we can also tell it can't really be of type ET either, because then it would not be able to compose with the verb except by predicate modification, and then we'd still have an unsaturated expression at the top. That would be of type ET. So the truth conditions and the types both tell us this cannot be of type ET. Well, if this is a type ET and this is a type T, there's not much left. Seems that all that's left then is type ETT. That is to say that a dog, the quantifying expression, denotes a function that takes the verb as its argument, even though syntactically it's the other way around. And well, if that's the case, then how do we build this? Well, this is of type ET. It's a dog. And then we'll take that and then build this very complicated expression. So it will take something of type ET and return something of type ETT. Now we can think about what that means. Right? What kind of expression is that? Well, let's work it out. It takes something of type ET. What is that? Well, it's a property. And then it takes something else of type ET. What's that? Well, another property. And then it says some kind of statement about them. So it takes two properties and tells us something about them. All right? What does it say? Well, let's look at the truth conditions. A dog is barking and a dog is at the door. A dog is barking, that's true, if and only if, what? Well, if and only if there is a dog, and that dog is barking. We don't have to know which dog it is, it's just there is one. So if a dog is barking is true anytime there is a dog and that dog is barking, then essentially it means that anytime there is an object, an individual, that's in this set, it's also in this set. Alright, now let's be a little more explicit about that. We've seen the truth conditions for a dog is barking. That would be one, if and only if there is an individual, so something in this domain, such that X is a dog and X is barking. Right? So it's a thing that's got both of those properties. Or you can say it's a thing that's in both of those sets. Or you can say that it's a thing, the thing that when you plug it into this characteristic function you get one, and when you plug it into this function you also get one. And so you plug it into this, we say X is a dog, we can replace X as a dog with the function dog of X equals 1. So we plug X into the function for dog and we get 1. And we can change that for barking too. Let's say barks X equals 1. Right? So if there is an X such that dog of X equals 1 and barks of X equals 1, then this sentence is true. Otherwise it's false. Now how does that get us our meaning for up? Well, we can think about it in a more general sense. This is the meaning of a dog is barking. But if we change out is barking with is panting, well, all we have to do is change this from barks of X to pants of X. If it's a dog is running, we change this to runs. And we can do that for any verb phrase, right? It doesn't really matter which one it is. So we can change barks of X to something more general. Let's say G, and then that would be an argument that we have to replace, with something. And whenever we have an argument of that type, of course, we'll have a lambda expression. The same for dog. It doesn't matter what this NP is, it's going to be that NP. And so we can do the same here, like F. And so we get the meaning of a general existential quantifier would be something that takes a function f and a function g and gives you 1 if and only if there is an individual such that f of x equals 1 and g of x equals 1. So if we give a function f and a function g, well, do we have that? Yes, we have a function f and a function g, and we end up with a statement, a truth value, in essence. 1 if this all holds and 0 otherwise. And so we've got our meaning. So right, we have these two different meanings, and what we want then is lambda f in d sub et. We want lambda g in d sub et. And then we want our sentence, which is 1 if and only if there is an x and so forth. Now we could write all this out, but we'll write it in an abbreviated fashion that reflects the way that these were written in predicate logic over decades and decades before when we did any compositions of this sort. So we replace there is an with a symbol that's called the existential operator. And it looks like a backwards E. And that stands for there is a, or there is an. So we say there is an x in d sub E such that f of x equals 1 and g of x equals 1. And so we get the meaning of in that sense. And that works out. And it doesn't matter what f is and what g is. Now you'll notice that something peculiar here. That the first argument is essentially going to be the meaning of the NP. That's going to work no matter what. And this is going to be, for now at least, the meaning of the VP. So it's going to say my NP of x equals 1 and my VP of x equals 1. That works out pretty well. Now what's interesting is that the NP is the first argument of and then the VP is an argument of the result, a dog. So semantically, the VP is the argument of the subject, whereas syntactically, the subject is the argument of the verb. So we get a mismatch in the roles, and that's perfectly fine. That's not a mismatch we have to worry about, because it doesn't affect the meaning of the verb. So this is how universal quantification gets formalized and how we get its meaning. In the exercises, we'll practice more of these. But that's how it's derived, right? We started with these truth conditions. We saw that existential quantifiers do not refer to individuals, they do not refer to sets, but rather they tell us about a relationship between two sets. And in that sense, we can get this meaning out of them. And by using the types, we can deduce that the meaning involves taking two functions and telling us something about them. And then it was a question of figuring out what those functions were. Well, the syntax tells us that. The first one is the NP, the second one is the VP. And then we just write it up like this. And we get our meaning for existential quantifiers. This works for and it works for some. And one thing we'll want to see is, can we get more fine-grained differences than that? But this is the starting point for all existential quantification, and we'll go from there.